Welcome to buffering capacity. So in the last video we introduced the concept of buffers, and we talked about how the Henderson-Hasselbalch equation can be used to calculate the pH of a buffer. So let's look at buffer capacity. So buffer capacity is the amount of an acid or base that can be neutralized by our buffer before there's a significant change in pH. And so this buffer capacity then depends on the concentrations of the acid and its conjugate base that are involved with the buffer. And the greater the concentrations are, the greater the buffering capacity. And generally, what we mean here is when we say before there's a significant change in the pH, we generally mean a pH change of 1. So if the pH of the buffer is, say, 4.5, we generally mean the buffering capacity is the quantity of acid or base that we have to add to change the pH from 4.5 either to 5.5 or to 3.5. So the pH range is the pH range over which our buffer is an effective buffer. And again, the pH range is generally within 1 pH unit of the pKa of our acid. So the calculation here can be broken down into 2 parts. When we add a strong acid or base to a buffer, we have a stoichiometry calculation and we have an equilibrium calculation. So in the stoichiometry calculation, the addition of our strong acid or base results in a neutralization reaction. We've got H plus A minus gives us HA, or we've got OH minus plus HA gives us water and A minus. So by knowing how much of our hydrogen ion or hydroxide ion is added from our strong acid or strong base, we then can know how much HA or A minus was formed. The second part is the equilibrium calculation. So with the concentrations of HA and A minus, taking into account the change in volume of our solution, then we can calculate the pH from the Henderson-Hasselbalch equation. So we plug in the base concentration divided by acid concentration. Again, we have to account for the dilution once we've added our strong acid or base. And so that was buffering capacity.